Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and I'm up to problem 2.38. 2.38 states, if alpha is a number between 1 and the square root of 1 plus e over 1 minus e, calculate the true anomaly at which the speed on a hyperbolic trajectory is alpha times the hyperbolic excess speed. So I'm going to draw a little picture of that. So this is our orbit here coming in, and here is our focal point. It is asking, there exists a point, say along this line here, that is, and this being velocity excess up here, and this being the velocity. It wants to know at what point is the velocity alpha times this, where alpha is between 1 and the square root of 1 plus e over 1 minus e. This is a funny equation because if you put e greater than 1 into this, you actually get a negative square root of a negative. So that gives you a complex number, which I don't understand. Maybe that's a mistake. I don't know. Anyway, it doesn't matter. In order to solve this problem, we can use the energy equation. So we can start with v squared over 2 minus gravitational constant over r equals v infinity square excess over 2. Now this bit here is also equal to gravitational constant over 2a, and we're saying that the velocity is alpha times velocity excess, so that means that velocity excess equals v over alpha. So if we take just this section here and we say, so that is v over alpha squared over 2 equals, now this here is also it's just a simplification of minus a half mu squared over h squared upon 1 minus e squared. And so we'll leave that like that, and then this side over here is v squared over alpha 2 alpha squared, and the v squared can be represented as the v radial and the v azimuth. So v squared is actually, the v azimuth is 1 plus e cos theta, so that's all squared, plus, so this equals v let's say radial squared plus v azimuth squared. This is v radial and this is e sine theta squared. This comes from the section in the book, this is true for all orbits, the flight angle path, mu squared over h squared, mu over h, squared. So these are mu over h 1 plus e cos theta, mu over h e sine theta, but it's all squared, so that's what we get there. Those are on page 72, 73, and that is, wrong way around. This is azimuth, this is radial, and then that's over 2 alpha squared, so that equals minus a half u squared over h squared 1 minus e squared. Now you may have already noticed this can cancel, so these are gone. This 2 cancels the half, so we end up with much simpler setup. 1 plus e cos theta all squared plus e squared sine squared theta equals minus 1 minus e squared, which equals e squared minus 1. So if we multiply all this out, we get 1 plus 2e cos theta plus e squared cos squared theta plus e squared sine squared theta equals e squared minus 1. This e squared cos squared theta plus e squared sine squared theta is equal to e squared, because we can pull out the cos squared theta and the sine squared theta, and cos squared theta plus sine squared theta equals 1. So we just end up with 1 plus 2e cos theta plus e squared. I completely forgot about the alpha squared. Forgot to move him over here. Right, there we go. Alpha squared. Going on from there, we can say that it is, well, it's theta equals cos inverse. Let's just move everything over and divide by 2e. So we have e squared minus 1 alpha squared minus e squared minus 1. That's it. Now, the answer given in the book is slightly simplified. Well, a bit neater. It gives alpha squared minus 1 upon e squared minus 1 minus 2. That does not look like that, but it actually is. If we just simply say and then if you take out, you make that a plus 1 and a minus 2, plus that's the same as minus 1. This section here will, when you group things together, you do actually get alpha squared minus 1 e squared minus 1 minus 2. If you multiply those out, you get that, right? So well, if you multiply both of those out, you get the same thing. So that ends up being that. That is effectively, answer is fine, but this is slightly simplified on the top line. 2e. So that's the solution to that. If you think I've made a mistake or you have any questions, leave them in the comments below. There'll be an example, MATLAB example of this equation in the description. Thank you. Bye-bye.